Hello, am I audible? You can hear me?
Yes.
Okay, perfect. So, do you have any questions from the last class? Let me share my screen and I'll open that file as well. Yeah, so we were solving some problems for circular motion. We were doing this problem, right? So I think we'll continue with this problem. And do you have any problems or any questions from anything that we have covered so far?
No, sir, no problems.
No problem. Did you get time to go through the topic that we have been doing? Have you gone through it?
Sir, I didn't have the notes.
All right. You're not making any notes while we're doing this. You can make notes. I don't mind. You can make notes, and I'll also share these notes. I also did not get the time because I have been a bit busy adjusting the schedule and everything. So but hopefully from next week things will be much more better and smooth. Do you just give me your opinion? Are you comfortable if the class happens in the morning? Like let's say it starts around like 9, 10 o'clock, 11 o'clock.
Sure, sir. Pakistan
No,
time?
there's no problem. Pakistan time, yeah.
Sure, sir, no problem.
Okay, that's great. Okay, so yeah, so I think we'll continue with this, and hopefully we'll even start the next chapter of gravitational fields today. So should we start this problem from the beginning, or do you remember what we were doing?
I remember, sir.
Okay, perfect. So we were about to solve this problem for phi, right? We wanted to find the angle if there is no tendency for the car to slide. So the car does, what is that optimal angle? Just say the car will not skid on this surface, right? So that's what we wanted to calculate. So the condition for no skidding is that the car must be in the equilibrium state, right? And if the car is in an equilibrium state, that means it will not slide up or down. So it will not accelerate or decelerate. And so in that case, the forces must balance each other. Is that cool, right? So if I resolve my forces vertically, then I have this r cos phi, and there is only this vertical and this vertical force, but they're opposite to each other. So I can write down plus r cos phi minus mg, and because this vertically the system is also in equilibrium, so this should be equal to 0, and this gives me plus r cos phi is equal to mg. So this is one of the equations, right? So is there any problem in this equation?
No, sir.
Okay, perfect. Then I can also write another equation using the what do you call that, resolving horizontally, right? So if I look at the horizontal components, I'm sorry, I forgot to make my screen a bit. I forgot to zoom it. I just realized. I apologize for that. So the horizontal component, you can see that there is only this one horizontal component, r sine phi, but this component is actually responsible for the centripetal force, right? Because this component is what is keeping this car in a circular orbit, right? And that have to be a horizontal component, right? A vertical component will not be able to keep maintain the what do you call that, centripetal force, right? Because that is the vertical component is dealing with balancing the weight of the car, and this horizontal component will balance the centripetal force part, right? So this part is contributing to the centripetal force. Hence, the centripetal force is actually the resultant of r sine phi. So from this, I can say that r sine phi is equal to the centripetal force. So I can write down that as mv squared over r. Okay, so that's cool. Because I did not use the other expression, which is mr omega something, mr omega square something. And the reason for that is because if you look back at your question, the velocity that we were provided with, that it's traveling on a track with tangential velocity, 32 meters per second. Remember? So I'll use the expression for centripetal force that involves the tangential velocity. So is this equation also clear? It's clear, this thing? I'll actually use small r for radius, because then this capital R, we're using it for the force, right? Okay, so if there's no problem in this part, so let's call this equation 1 and let's call this equation 2. And let's basically, we don't know the value of R, right? So we don't know what R is. So I need a method so that I can eliminate R. So what I can do is I can divide equation 2 and 1. So what I'll do is take equation 2, divide it by equation 1. So that means what I'm doing is equation 2 is r sine phi is equal to mv squared by r. We'll divide this by equation 1. So equation 1, we have left hand side r cos phi. So that's r cos phi. And we have on the right hand side, we have mg. So mg, which eliminates r, and it gets rid of the mass as well. And we're left with, well, what is sine over cos? From mathematics and trigonometry, we know that that's simply tangent. And we have angle phi. This is equal to v squared over r divided by g. So that becomes v squared over g times r. So that's the equation now. I should have not used equal to sign, just put this arrow. And this is our equation. From this, we know the radius r. We know this. We know the velocity. It's given in the question. The value of g is also known. And we can just simply take the tangent inverse of this thing and compute for phi. So let's do it over here. Phi will be tangent inverse of v squared, which is, well, it's just a matter of putting the values, right? So radius is 120 meters and velocity is 32 meters per second. So 32 meters per second squared divided by, we have g, which is, let's just use 10 meters per second squared. And then we have r, which was, I forgot, it said 120 meters, right? So we have 120 meters. Now just evaluate this and you get 41 degrees. Now, what is this 41 degrees? This 41 degrees is that particular, or it is that optimal angle on which, if I incline this track at what was the angle I got? 41. If I incline this slope or track at 41 degrees, in that case, the car will maintain an equilibrium state while it moves on this track, right? In the circular path, it will move on the track on the circular path, but it will not skid up and down the road. So that's how the racers or whatever, they maintain their vehicle without skidding, right? So they can speed up without skidding. Is this cool? Is there any problem in this part A? Okay, perfect. So Sounds great. Now, let's read what was part B. Okay, suggest and explain what would happen if the car's speed was reduced. So the speed is being reduced. Any idea what would happen? I'd like to hear your opinion. What would happen if the car's speed is reduced?
The angle would decrease.
Well, the car is moving. This is the ground, right? So if the speed of the car decreases, it will not basically affect this level of the ground, right? So the angle would not be affected. But nice try. You can think of something else. Do you understand why the angle will not decrease, by the way? Because this is the slope on which the car is, right? So it's just it's a concrete kind of thing, and like
It
this
is a
cannot.
fixed slope.
Yeah, it's a fixed slope, exactly. So anything else that could happen? Think in terms of the centripetal force. It's mv squared over r, right? So we're saying that the speed slows down. So that means v would decrease.
So the centripetal force will also decrease.
Yeah, exactly. So the centripetal force will decrease, which means that the car would basically slip down, because now the required centripetal force is not being met, right? So now the centripetal force has decreased, so it's not at its optimal level to keep the car moving without skidding. So the centripetal force will decrease, and so the car would basically skid down. So is that clear? Why would the car fall a bit lower? Or it would move, you can say in this diagram, it would move a bit to this side.
Yes, sir.
Because, yeah, so the centripetal force has been reduced. Okay, so, right, so perfect. So I think that completes this thing. And I don't think we have any more. So for now, this completes the circular motion part. Let's start the next chapter, which is of gravitation. Do you have any, because you did not get time to, and I did not even share the notes with you. So I think I'll share these notes with you as soon as possible, right? Let's see, I'll try it today. And you can let me know if you have any problems or anything. We can discuss it in next class as well, right? And on Friday, we'll solve more problems regarding to this first chapter that we have completed, and we'll hopefully try to complete this chapter as well by Friday, and we'll solve problems. So yeah. So, but is there anything on your mind before we start with this chapter?
No, sir.
Okay, perfect. So the next chapter is gravitation, and it's actually a very do you have any idea about, have you gone through, have you read, or is this your first time?
About gravity, sir?
Yeah, about reading this chapter of gravitation from your A-level syllabus. Have you gone through this topic before?
No, sir. It would be the first time.
It would be the first time. So I guess let's start it in this way. 1 second. Let's fix this. So basically, the idea is, I'm sure you know all the story behind it, how Newton wrote down the laws of gravity, the question that he proposed. He asked himself that if the apple fall, why does the moon does not fall to the earth, and all of those things, right? And so basically what Newton gave us a law for a force of gravity, which is, we'll talk about this in detail, but it's minus gmm by r. I think it's minus gmm by r squared, right? So this is what Newton gave us, but Newton himself did not know what is the source of this gravity. So if you think about it, we have sun and we have earth, which is orbiting the sun, right? It's orbiting the sun. There is nothing that is attached between the two, right? So it's not like there is some string that is keeping this earth in a circular motion around the sun, right? There's nothing like that. So it was very confusing. It is very weird to think of it that there is some action at a distance happening. So there's nothing that is connecting these two things, but there is still, the earth still feels the effect of this sun, right? The force of the sun, you can say. And so it turns out that we can use Newton's laws for the most part, but Newton's idea, they had a problem, and they are not the correct rules, but they work, and they work for the most part of it. But the true nature of gravity is it's a geometry, right? So it's not a force. It's not a force like you experience electromagnetism, for example. It's not a force in that sort of a way. It's actually the geometry, and the geometry comes from something that is called space-time, right? So Newton did not know about this, and so he did not know what was the source of gravity. But the source of gravity is space-time itself. Now, it's a weird thing, but space and time, they are, you can say that these two are one object. Space and time is not separate, but it's one object. And it might seem weird at first, but let me give you an example. Whenever you have to go somewhere, for example, you call your friend and you decide to get together, meet up, or whatever, right? So you decide a place, but can you just tell them that, come at this place? They'll ask you for more. What would they ask you for? What is the other piece of information that you need to tell them to make this meeting happen?
Directions.
Directions and everything is given. Let's say, you give them the direction. You say that you have to meet at this place. Okay. For example, you're meeting at, let's say, Pizza Hut. You're going to meet at Pizza Hut, or just an example, right? What else do you have to tell them to meet at Pizza Hut? You have just tell
specific location.
Yeah, the specific location part is done. The other thing is time, right? It's time, because unless you specify when are you going to meet them, the meeting may not even happen, right? So you agree with that, right?
Yes, sir.
Yeah, so you would have to tell them the location, exactly like you said, the location, but you also have to tell them time. Without these two things together, you will not be able to meet. And that's fascinating, because if you think about that, this means already space and time have been always connected, but you never thought about it in this way. We never thought about it in this way before. But if you think about this example, it seems very obvious that yes, space and time must be connected, because one does not really give you that much information without the other. And that's pretty fascinating, right? So that's the idea of space-time, and these space-time basically curves, it bends, and it performs all these things that you can do with something that is malleable. So space-time is malleable, and you can bend it, you can curve it, and that's why we experience gravity, because of the bending of space and time. Now, space-time bends in a sort of a very weird way. maybe you have seen some videos on YouTube or something, but it's not really like that, because those are 1 or 2 dimensional things, but space-time is something that is a 3-dimensional thing, and actually 3 spatial dimensions. So there are 3 dimensions of space, and 1 dimension is for time. Anyways, we're getting too ahead of ourselves. These are some of the interesting factors, things that so basically gravity is a very fascinating topic actually. So anyways, I think we should get into the topic now. So first of all, we need to understand what is a field. Before we even talk about gravitational field, we need to have an understanding of what is a field. So now you'll see many definitions for a field. So a field, mathematically, you can say that a field is it's a set, right? It's a set on which you can perform addition, subtraction, multiplication, and division. So it's a set where all of these operations are defined, and they behave as operations on real numbers, on real or rational numbers, right? And that's something that a mathematician would call a field. For a physics point of view, we can just say that a field is something, let me write it down as well, it's something which takes values at every point. At each point, right? Now think about this. Think about temperature in a room. Let's say this is a room, right? Let me just draw. So this is a room, and let's say that there is a window over here, right? So this is a window. Now in this room, let's say there is some fireplace over here as well. So there is fire, and just ignore my drawing, but this is just some fire. Now if I were to sit or stand in this room and measure temperatures, so I'd have at every point there will be a value for temperature, right? So if I measure with my thermometer or whatever, I measure it near this fireplace, the temperature would be high, right? You agree with that, right? So the temperature near this fireplace would be very high, right? You agree with that, right?
Sir, can you explain it again, please?
Yeah. So basically, I was giving an example of a field. So I just said that it is something that will take values at every point in space. A field is defined as something that takes a value, a number, a constant at each point in space. So I said, let's consider this room. There is this room, and suppose, for example, it has a window at some point, at some place, and there is a fireplace at some place. So there is some fire over here in this room, right? So when you measure temperatures near this fire, if you pick this point and you put your thermometer at this point, the temperature would be high, right? Near a fireplace, the temperature would be high. So you agree with that, right?
Yes.
Okay, perfect. And similarly, if I measure it somewhere over near the window, the temperature would be low, it would be cooler. And somewhere in between, its temperature would have some different values, right? So you get this concept of temperature would take different values at each point in this room. Is that clear?
Yes, sir.
Exactly. So temperature is a field. And what we were talking about all this time was a temperature field. So at every point in this room, you can assign a value. And so what we were measuring was temperature, and hence that was a temperature field, right? Similarly, now we can talk about gravitational field. So basically, a gravitational field is a field in the similar manner. So suppose that you have, this is your space, and in this there is this gravitational field, and the space is filled with gravitational field. Now when you put an object in this field, suppose there you have this object, let's call it, this is the sun. So what happens is this mass will basically, you can say it would give rise to the gravitational field, such that if suppose that gravitational field will have effects only in this region, this what do you call this, this rectangle that I drew. So the gravitational field can only affect this much part that is coming due to the sun, and that's because of the inverse square law, which we'll get into it. But if I put an object over here, let's say this is the Earth will experience this gravitational force of the sun simply because of the fact that when the sun was sitting in this space, it produced gravitational field, which if I put this object, if I put the Earth near this sun, then it would experience this gravitational field, and hence it would fall into the orbit of the sun. So that's why the gravitational field strength is defined as a gravitational force per unit mass at any particular point.
Would the gravitational field acting on both objects be constant?
The gravitational field acting on these two objects,
Yes, sir.
yeah, it would be constant, right? So basically what would happen is, if I have this sun, suppose that it's a sun, when if it's sitting in space, it would basically produce a gravitational field. And then I put another object, suppose this is Earth, I put Earth in that gravitational field. Earth would also create its own gravitational field, but it will also be affected by the gravitational field of the sun, right? Because of course, Earth or sun, none of them is special. If the sun is creating a gravitational field, what it essentially means is that any mass that I put in space would create a gravitational field, right?
Yes, sir.
Okay, so now the gravitational field strength, the strength of the gravitational field, it would be greater near a massive object, right? So for example, if I have this sun, the gravitational field strength would be higher where you have a more mass, right? So that was what I was trying to get across, because gravitational field strength is then related to mass. Because if anything that has mass and it sits in space, it produces gravitational field. Now the strength of that field depends on how massive my object is. The more the mass it has, the more gravitational field strength it would produce. So that's clear, right? And that's the reason that the sun has a higher gravitational effect, right? Compared to, so for example, we have sun, we have Earth is orbiting the sun, then the moon, it's orbiting the Earth, because for moon, it's closer to the Earth and it orbits the Earth because Earth also produces some gravitational field. And you can even find the orbital radius for moon. So for example, you know that even your Earth, it's surrounded by lots of space junk, basically. So whenever you have astronauts, they go in space, they have to eat and everything, right? So when they get rid of those materials, they just put them out in space, and then our space, the orbit of the Earth, it's filled with a lot of junk. And that's there because it is those junk, they have mass. So for example, you could have a wrapper of chocolate, you could have a wrapper of chips or anything of that sort, right? Because it has mass, it is affected by the field that was produced in the space due to the Earth. So is that clear, the idea of gravitational field?
Yes, sir.
Okay. So now we can move on to the Newton's law of gravitation. And the Newton's law of gravitation basically says that if you have two masses, so if let's say this is a mass and you have another mass, so these are two different masses, there will be some place or there will be some extreme points, you can say, where these two would feel the effects of each other. So in such a way that these masses would basically attract with each other. And the further that I keep moving these masses, the less the force effects that these will experience on each other. And that is dictated by this inverse square relationship. Let me use this one, 1 over r squared, right? So increasing the distance would decrease the force, right? So increasing distance would decrease force, you can say 4 times. So if you increase the distance by 2 times, the force would decrease by 4 times because it is r squared, right? So is that point clear?
Yes, sir.
Okay, so that's what happens, right? And you can mathematically write this down with this expression: F is equal to G mm by r squared. So what's happening is actually there should be a negative sign over here as well if you do not include the I think when writing this down they have included this this thing, what do you call that, the sign for the direction of r as well in this r squared. But let's say that there is no direction, then you have to input this minus sign, and I'll explain why there is this negative sign as well. But so the force is actually proportional to, because as we said about the gravitational field strength, the more massive, the more the gravitational field strength. And if gravitational field strength is more, that means the force would be more, right? Because it would experience more effects of gravity, and hence the force would be higher. So the force is proportional to the masses of the object. So let's say if it's m or if it's m, right? So both of the masses, the force is proportional to those masses, but it is inversely proportional to the distance between those masses. So this r is basically the distance from this to this mass, the center of that mass to the center of this mass. That's r. And so once I have to write this equation in terms of equality, equal sign, so I have to introduce a constant which is known as g, which is the universal constant of gravity, right? Or it's the actually it's written over here, I don't need to write it down. So it's the universal gravitational constant.
Sir, what is the difference between the small m and capital M?
Right, exactly. So one of the mass is so it's basically one mass is for one object and the other mass is for the other object. Think about this. We're talking about force of gravity. So it appears in pairs, right? So there has to be, if there is one mass, it has to be attracted to another mass. So there is this pair of two masses, right? So one of the m, and they're being multiplied, so the order does not matter. If I put this here or put this here, it doesn't matter. So because they are being multiplied, right? So one mass, you can sometimes, it's also called that m is the source mass and small m is the test mass. Okay, I'll tell you the reason for this. So for example, you have the sun over here, and then you have Earth, which is orbiting the sun. Then I can say that capital M is the mass of the sun, because sun is the source of gravity which this Earth is experiencing. So that's why M is referred to as source mass, and small m is the mass of the Earth, which is a test mass. So you're just testing that mass, because you could have picked any other mass. So for example, there was Venus, planet Venus over here. It would have some mass. So any mass it would have, that's also a test mass. But because both of these planets are under the influence of this source mass, gravity, so that's why capital M is also called the source mass and small m is called the test mass. So is that clear?
Yes, sir.
Perfect. So let me check how much time do we have left in this meeting.
4 minutes.
Can you 4 minutes? Okay, so let's see how much more we can cover. And right, so is the idea of this Newton's law of gravitation clear?
Yes, sir.
Okay. So next is that deriving Newton's law of gravitation. So gravitational field strength at a point is already defined, right? So now you know the gravitational field strength. What does it mean to be defined at any particular point in space, right? So it's actually the gravitational force that the object will experience per unit mass at that point. Now, so then you can write it, it's actually written over here, you can write it mathematically as G is equal to F over M. Why? Because as we have defined it, it is the gravitational force per unit mass, and we give it a symbol small g. This is the same G that we have as equal to 9.81. We have been using it for a very long time now, right? So it's that same G. So that's the gravitational field strength. So the number 9.81 meters per second squared is telling you the strength of the gravity. So the higher that number is, the more force there would be between the two objects, right? So that's why on moon, the number is smaller compared to the number on the earth. And that's why on moon, when you jump, you can easily, you can, well, I don't know how to say it, but you can float and all, right, easily in moon compared to on the surface of the earth. So if this is G, which is equal to F by M, then by the Newton's law of gravitation, we know that we wrote it up over here. It's defined as this GMM by R squared. I can put this value in this expression, right? So upon doing so, we get G is equal to GMM by R squared into this 1 over M, right? So this cancels and we're left with this expression. And hence, we can say that the gravitational field strength of any mass is defined with this equation. G is equal to Gm by R squared, where M is the source mass. So you can see what happened over here is that the test mass was eliminated from the equation. So the test mass does not matter. And that should be obvious, because the source mass is creating the gravity which any other mass around it would experience. So the field strength of gravity should only depend on that mass that I put in there in the first place, which is producing the effects of gravity. So if you think of this example where you had the sun, so the gravity that this earth would experience is coming from the mass of the sun. The mass of the earth does not matter, right? Because earth is experiencing the gravity which was created by this mass of the sun. So is that clear?